CIT 1124, Module 12, Submodule 4, CapWAP operation. We'll also do Module 5, which is channeling. So let's take a look at CapWAP for a second. CapWAP's fairly, compared to the rest of the technology that we're going through in this chapter, pretty new. It is a solution to allow a wireless controller to manage many access points at the same time and allow those access points to retrieve information from multiple wireless LANs so that you can have, just like we have at the COD, there is two wireless networks everywhere you go. That doesn't mean there's two different antennas. There's one antenna, two wireless networks that are controlled by a wireless controller someplace else. So we don't have to put the logic in all the antennas. We'll have it in one place. Now, when we send that logic back and forth between the devices, we want it to be secure. So that brings up another solution that we need to be aware of, the Datagram Transport Layer Security, the DLTS, which allows us to securely pass the data information from the wireless controller to the wireless access points and back from the wireless access points over to the wireless controller. It is a UDP protocol. It's something newer and more efficient. The original concepts behind these was to build VPNs between all of these devices, and this is it's a lot more efficient actually. So it's the newer solution that you'll see if you end up going out and buying these Meraki access points or some of these other brands that need this service. You can work with it. Okay, this slide just kind of gets into the little cloud there of there's controlling data, and then there's actual data that wants to be sent. We're going to go ahead and encrypt all that because we don't want people ripping off and seeing everything that we're sending through these solutions. So we're going to go ahead and secure that information. The next section we want to talk about in this particular video is channel management. And when they get into channel management, they talk about three different types of frequency channel saturation. There's something called DSSS, Direct Sequence Spread Spectrum. This is the origination of what 802.11 used to do. And this is based on the idea that we can run a low amount of signal across a wide spectrum, and it'll be picked up by another device. And I'm going to sneeze here. Excuse me. Sorry about that. And 2.4 gigahertz space, ideally, and you'll be able to pass frequency back and forth, or signal back and forth, based on just the amplitude of the wave itself. So we're going to tune into the frequency, and then depending on the height of the wave, we'll identify these either we'll interpret it as a 0 or a 1, right? We'll have low flying waves with low amplitude, and those will be zeros, and higher waves. Excuse me. Higher waves, and those will be ones, and just be aware of that. Let's skip over frequency hopping for just a second and get into orthogonal frequency division multiplexing, which is what they use now, and this adds another value called phase into the system. So instead of sending just one bit at a time like we do in DSSS, in OFDM what we can do is we can add a phase value. So a frequency that we tune into is going to be okay to receive the information, and then we'll measure the amplitude, but we can also add 4 other values as for phase. So we can add a phase value and interpret a phase and an amplitude, and between those two we can come up with, we can send 4 bits of information at the time that we used to send 1, and that's way faster. So that's the main idea of what OFDM does for you. The other one is frequency hopping spread spectrum, which is just a method where you can use it's called a signal carrier code, and you can send this code to another device, and it'll know where to listen to retrieve the information specifically that is being sent. So we'll send a code and say, listen at this substream or at this subchannel, and then go to this subchannel, and then go to this subchannel. And each time you're at one of these, you have a period called a dwell time. So you'll dwell, you'll listen, you'll receive, you'll hop around to another frequency, you'll dwell, you'll listen, you'll receive. You hop to another frequency, you dwell, you listen, receive. It's the same thing over and over again. So we send basically a chart on where to go, and then if anyone that doesn't have the chart, they'll have a hard time reading whatever that solution is. Bluetooth is based on this frequency hopping spread spectrum technology. And OFDM and DSSS are more of the 802.11 wireless LAN technologies. The next two slides just show the 2.4 gigahertz bandwidth space and how it's divided up. And there are 11 channels within that space. And you can see there is a little bit of overlapping. So if you're going to use channels within 2.4 gigahertz, you'll use channels 1 and 6 and 11 because that creates the least amount of overlap between the three. That's represented by the golden arches. I'm suddenly hungry. The golden arches down on the diagram below where you can be in 1, and 1 will not intersect with signal at 6 and so on and so forth. If you think about old school television channels, same kind of thing. In Chicago, we had 2 and 5 and 7 and 9. Weird that we never had a channel 5 and 6. Well, the reason for that is because channel 5 signal will bleed into channel 6 and into channel 4, and channel 7 will bleed into channel 6 and channel 8. And so it's just better to kind of spread them out a little bit, and you'll get a cleaner signal if we keep them away from each other. So we have the opportunity to put stuff on every channel, but it's better if we just use 1 and 6 and 11 if possible, or 1 and 3 and 8 and 11 if possible, if you need 4 channels to utilize. So it's just a matter of kind of taking the space that's been allowed for us or as amateur radio engineers and allowing us to create space for other devices that'll be in the same range. Okay. Same thing is true of the 5 gigahertz space. There are a whole bunch of channels, and you can use different numbers of channels. They're separated by 20 megahertz, and this just kind of gives you an idea of what that looks like.